already holding back billions of gallons of water, work done on the Gross Reservoir Dam is the footwork for a lot more.
High above a narrow canyon in Colorado, a quiet wall of concrete has held back a restless reservoir for generations, carrying the weight of cities that grew faster than anyone predicted. Decades later, engineers returned with an audacious plan.
And really, it behaves as a replacement for rock. So the nooks and crannies are filled with concrete that really replaces the rock and gives us a uniform surface for the dam concrete.
Not to replace it, but to fuse new strength onto old foundations, turning a mid-century dam into a world record experiment in survival and scale. Sleeping Giant, a dam built for another era. When Gross Dam first rose above South Boulder Creek in the 1950s, it embodied the quiet confidence of post-war American engineering, a concrete arch designed to capture snowmelt from the Front Range and deliver it steadily to a growing Denver metropolitan area. At the time, planners believed they were building for generations, calculating storage volumes, spillway capacity, and seismic resilience according to the best hydrological data available, confident that the region's future could be forecast with slide rules and paper maps. The structure, completed in 1954, stood roughly 340 feet tall and held back a reservoir that quickly became a lifeline for farms, neighborhoods, and expanding suburbs across Colorado's northern corridor. For decades, the dam performed as intended, quietly moderating seasonal floods and storing winter runoff for the dry months that define life in the American West. Families moved into new developments with little thought about the invisible wall holding back billions of gallons of water upstream, and city planners approved new housing tracts, assuming that storage capacity would continue to meet demand. Yet, beneath that confidence, the arithmetic of growth began to shift as population surged, drought cycles intensified, and climate models suggested that snowpack patterns might no longer resemble the historical averages engineers once trusted. By the early 21st century, Denver water faced a dilemma that was not dramatic, but deeply structural. The region's water security depended on infrastructure built for a different era of climate stability and smaller communities. Replacing the dam entirely would have meant dismantling a functioning system and exposing downstream communities to enormous risk and cost, a path that few considered realistic. Instead, the question slowly crystallized into something more complex and more daring, forcing engineers to confront whether a mid-century concrete arch could be transformed rather than abandoned to meet the demands of a far less predictable future. The problem no one could ignore. As population in the Denver metropolitan region continued to climb, Denver Water's long-range planning studies began to show a widening gap between projected demand and reliable supply, especially under drought scenarios that climate scientists warned could become more frequent and more severe. The utilities modeling, built on hydrological data and climate projections, indicated that existing reservoirs might not provide sufficient buffer during prolonged dry cycles, particularly if snowpack declined or runoff timing shifted earlier in the spring. What had once been a comfortably engineered margin of safety began to narrow, not because the dam was failing, but because the assumptions behind its design were aging alongside it. Replacing Gross Dam outright would have required draining or bypassing a critical water source, demolishing a structurally sound arch, and constructing an entirely new facility in steep, environmentally sensitive terrain. Such an approach would have triggered enormous financial costs, complex federal and state permitting hurdles, and prolonged service disruptions, all while exposing downstream communities to temporary vulnerabilities during construction. Expanding storage elsewhere posed similar challenges, as suitable dam sites are rare, and public opposition to new reservoirs has grown steadily over the past several decades. Engineers and planners therefore confronted a question that felt at once pragmatic and radical. Could the existing dam be raised, effectively increasing its height and storage capacity without dismantling the original structure? Raising a concrete arch dam is not a simple matter of stacking more material on top, because the entire structure must redistribute loads, resist uplift pressures, and behave as a unified system under seismic and hydrological stress. The proposal would require attaching modern materials to mid-century concrete in a way that allowed old and new to function as one, a task that moved the conversation from incremental upgrades into the realm of structural reinvention, engineering the impossible. Raising Gross Dam was never a matter of simply pouring additional concrete along its crest, because the structure was designed as a thin arch that transfers immense water pressure laterally into the canyon walls, not vertically into a broad base. Any increase in height would amplify the hydrostatic forces pressing against the face of the dam, altering stress distributions throughout the original 1950s concrete and the abutments anchoring it into bedrock. Engineers from Denver Water, working with firms such as Stantec and Kiewit, had to determine whether a mid-century arch could safely accept a modern extension without compromising its integrity. The solution centered on roller compacted concrete, or RCC, a material developed in the late 20th century that behaves more like a carefully engineered, zero-slump concrete placed in layers and compacted with heavy rollers, similar to asphalt. RCC allows for rapid placement in thick lifts, creating dense, durable mass concrete with lower cement content and reduced heat of hydration, which minimizes cracking in large pores. In practical terms, it meant that instead of casting massive monolithic blocks in forms, crews could build the rays in horizontal layers, compacting each course to achieve strength and cohesion while controlling thermal stresses. Yet the material alone did not solve the central challenge, because the new RCC section had to bond structurally to the existing arch so that both would respond as a single unit under load. Engineers drilled and anchored steel dowels into the old concrete, prepared bonding surfaces, and designed a geometry that allowed the new upstream face to integrate seamlessly with the historic structure. Detailed finite element models simulated how the combined dam would behave during extreme flood events and seismic shaking, ensuring that the old arch and the new rays would share stresses rather than compete against each other. As plans matured, it became clear that this was not merely a height increase, but a structural graft, a deliberate fusion of two generations of engineering separated by nearly 70 years. That realization set the stage for what would soon be recognized as something unprecedented in modern dam construction: the world record raise. As construction began, what had seemed like a regional infrastructure upgrade took on global significance, because the Gross Reservoir expansion would become the largest raise of a concrete dam ever undertaken using roller compacted concrete. This was not simply a matter of adding height, but of executing a world record scale structural transformation in which more than 500,000 cubic meters of RCC would be placed against a 1950s arch, effectively increasing the dam's height by over 100 feet and dramatically expanding its storage capacity. In engineering terms, the project represented a test of whether modern mass concrete techniques could safely extend a mid-century structure without undermining its original design logic. The scale of the operation reshaped the canyon itself, as batching plants, conveyor systems, and access roads were constructed to support continuous placement of concrete in carefully sequenced lifts. Each layer of RCC had to be compacted to precise density specifications, with temperature monitored to prevent internal stresses that could propagate cracks over time. Meanwhile, crews worked methodically along the contact zone between old and new concrete, ensuring that anchors, shear keys, and bonding treatments performed exactly as modeled in design simulations. Raising an arch dam alters more than its silhouette against the skyline, because every additional foot of height increases the water pressure exerted at the base and along the abutments. Engineers therefore revisited structural analyses repeatedly during construction, validating that measured deformations and stress readings aligned with predictive models. Instrumentation embedded within both the original dam and the new RCC section transmitted data on strain, temperature, and movement, creating a live feedback loop between field conditions and design assumptions. By the time the crest began to climb visibly higher above the canyon rim, the project had moved beyond symbolism into proof of a concept. If successful, Gross Dam would demonstrate that aging infrastructure need not be demolished to meet modern demands, but could instead be re-engineered at a scale once considered impractical. That possibility reframed the project from a local necessity into a case study watched by dam owners and engineers around the world: pressure, risk, and the human stakes. Behind the statistics and engineering diagrams, the expansion unfolded under intense scrutiny because altering a major dam in an era of environmental awareness carries consequences beyond structural calculations. Environmental groups questioned increased diversions from the Fraser River Basin, arguing that added storage could affect ecosystems and downstream communities. Public hearings, regulatory reviews, and mitigation measures became as central to the project as concrete placement itself. Technically, engineers modeled extreme flood scenarios and seismic forces to ensure the raised dam would withstand conditions beyond historical records. Spillway capacity, freeboard, and structural stresses were re-examined under conservative projections, while embedded instrumentation monitored strain, uplift pressures, and temperature in real time. These measurements transformed theoretical models into verifiable field data. For crews working along steep canyon walls, the risks were immediate, demanding strict safety standards and uncompromising quality control. As construction progressed and concerns were addressed, the project gradually moved from controversy toward cautious acceptance, reframing the raise as a long-term safeguard against future water uncertainty. What this changes for the future. When the raised crest of Gross Dam settles into Colorado's skyline, it represents more than added storage. It signals a new philosophy of infrastructure adaptation. By expanding reservoir capacity, Denver Water strengthens drought resilience for a region facing increasing hydrological uncertainty. The project demonstrates that aging dams need not be replaced outright, but can be structurally reinvented through modern materials, advanced modeling, and rigorous monitoring. By integrating roller-compacted concrete with a decades-old arch, engineers show that legacy infrastructure can evolve responsibly. In doing so, Gross Dam becomes a case study in building resilience for an unpredictable future. Concrete does not forget the era that shaped it. Yet at Gross Dam, engineers have proven that even a 70-year-old wall can evolve when necessity and ingenuity meet. As climate and cities change, adaptation becomes the quiet measure of survival. If this story reshaped how you see infrastructure, subscribe and continue exploring the forces that hold our world together.